Hi, hello, good evening, one and all. Welcome to the session. Welcome to BYJU'S exam prep. Can anybody confirm about audio and video? Is this audio and video both are clear? Hello, guys. बताइए audio video ठीक है क्या? Please do let me know about this audio and video. All right, fine. It seems to be fine. Let me check from my side. Okay, done. So in the last session, we had a discussion on voltmeter, ammeter method, and ammeter voltmeter method. All ammeter voltmeter method and voltmeter ammeter method, we use this to measure the DC power. By the way, okay. So if you want to use ammeter voltmeter method, it is better suitable for low resistive loads DC power measurements. And if you want to use voltmeter ammeter method, it is better suitable for load resistance low value, and this is load resistance of high value. Okay, right. So in both the methods we have got some errors. The error in ammeter voltmeter method and the error in voltmeter ammeter method, we have got it. So the error in ammeter voltmeter method was like VL square divided by RV, and the error in voltmeter ammeter method is IL square into RA. Remember, if you look at this one, this error component is because of voltmeter. This error component is because of ammeter. So whatever the meter which is near to the load side or near to load, that meter will give you the error. Now the question is, at what point of load resistance, both the errors are going to be equal. So if we have equated this and we try to get the answer as RL is equals to under root of RA and RV, geometric mean of RA and RV. So okay, so this was the last session discussion we had okay. Now in this session we will be discussing about measurement of single phase power. So we have seen DC power. Now let us take up single phase power. Okay, right. So I wanted to convey one point here. To measure the DC power, we are using ammeter and voltmeter, otherwise voltmeter ammeter. We are using two meters, right? So one meter is measuring current, another meter is measuring voltage. Now, why can't you design a meter? Why can't you design a meter which can measure both voltage and current, and it should give you the power component directly? Okay. So the power is actually in a AC circuit or in AC system, the power is actually complex power. Okay. Complex power. So one will be having an active component, one component will be active component, another component will be reactive component. So you need to design a meter, to measure the useful component. Generally, we will be designing a meter to measure the useful component. That is called active component. Of course, no problem. Of course, no doubt. You can also design a meter to measure the reactive component also. But mostly our discussion will be with respect to active component of power measurement only. Okay. So whatever the discussion we are going to have in this session, is all about measurement of useful power only. Okay. So yes, so we'll move on. So can you please let me know about your presence so that we can move on. Before moving on to the session, this is a small introduction. Those who are very much new to the platform, BYJU'S exam prep platform, welcome to the BYJU'S exam prep platform. Myself, Naveen, I have 11 plus years of experience in teaching. I did my masters in electric power system from JNTU Hyderabad. I cracked GATE and State Public Service Commission examinations too. I taught more than 20,000 students since 2012, and most of the times I'll be taking electric circuits, machines, measurements, and power systems. So these are the subjects I'm going to take up on the BYJU'S exam prep platform. Right. So here is a small announcement about the engineering services mains examination or engineering services aspirants. those who have got, those who have qualified in engineering services mains and those who have qualified for, shortlisted for interview. So BYJU'S exam prep platform is, conducting mock interviews. You can check out this. If you are interested, you can check out with this one. Or if any one of your friends are, preparing for mock tests, you just inform them so that it will be benefited for them. Okay. All right. So moving on here, I wanted to measure single phase power. Single phase system, generally we will be having phase and neutral. Phase and neutral. So this is my supply terminal. This is my supply voltage. Let me take up it as V supply. Okay. Generally we write it as V of t, instantaneous voltage V of t. Okay. Now I am connecting this supply. I am connecting this supply to a load. To a load. Maybe the load can be a fan load or refrigerator load or any AC load. You can take up any load, whatever you want. Generally, the load nature is going to be resistive nature and inductive nature. That is why we call it as lagging load. I am taking a lagging load. Okay. Now for this load, I just wanted to measure what is the power consumption by this load. What is the power consumption by this load? Okay, what is the power consumption by this load? Okay, so here if you want to measure the power consumption by this load, you need to place voltmeter to measure the voltage across the load, and you need to place an ammeter to measure the current, load current which is flowing through the load. Okay, but generally already we have seen the discussion, already we had a discussion about this voltmeter and ammeter method, or ammeter and voltmeter method. It is every time you get the readings and every time you need to product them, you need to go for mathematical calculation, that is product calculation. A manual interference is required, right? So you just place a meter such that it has to give the power measurement, right? Every time looking at voltmeter and ammeter reading and getting the power measurement, it is not good. Okay, so design a meter such that it has to give the power consumption by the load. So you need to place a meter. You need to place a meter such that it has to measure the power consumption by the load. So what should this meter should consist? What this meter should consist? This meter should consist a coil. This meter should consist a coil to measure the voltage, and this meter should also consist a coil to measure the current. Okay, so that meter is actually basically electromagnet moving coil instrument. So this meter is actually electromagnet moving coil instrument. So this meter is going to measure the power. Okay, this meter is going to measure the power. So let us see, first of all, let us see without meter what is the power we are going to get. Let us see first. Without meter, what is the power measurement by the load, we will see. Okay, so here whenever you connect a voltage source, it is going to drive a current I of t. Okay. Now I can write the instantaneous voltage into instantaneous current. We will be getting instantaneous power. First of all, let me write here what is V of t, instantaneous voltage. I can take it as Vm into sine omega t plus theta V. Okay, you can convert this into polar domain also. You can write this into polar domain as Vm at an angle theta V. Similarly, I of t is equals to Im into sine omega t, plus theta I. Okay, you can convert this into polar domain, that is phasor domain, Im at an angle theta I. Okay, so what does it mean? Voltage phasor is leading from the reference axis at an angle of theta V. Current phasor is leading from the reference axis at an angle of theta I. If you represent, it will look like this. If I take up reference axis, now the voltage phasor may be here, V, and at an angle of theta V. The current phasor may be like this at an angle of theta I. Okay, no doubt, no problem. Even you can write current as much leading than the voltage also. Here I have taken current as lagging with respect to voltage. You can take up current leading with respect to voltage also, no matter. Okay, no matter. Right. So this is how the phasor representation is going to be. Okay, fine. Now let us go for the calculation. If we go for the calculation, the instantaneous power P of t is equals to V of t into I of t. Okay, if you solve it, like I'll be getting Vm into Im into sine omega t plus theta V into sine omega t plus theta I. It is like sine A sine B component, right? It is like sine A sine B component. Now let us make it as 2 sine A sine B. I am multiplying and dividing with 2. So 2 sine A sine B component, I can write it as cos A minus B minus cos A plus B. Now, okay, cos A minus B minus cos A plus B. So this is, you can take up it as A term, and this is, you can take up it as B term. So if you write this one, you will be getting like, you will be getting as Vm Im by 2. So 2 sin A sin B, I am writing it as cos A minus B, cos of A minus B, omega t plus theta V minus omega t plus theta I. So omega t can be cancelled. Now I will be getting theta V minus theta I. Okay, minus cos of A plus B, cos of A plus B. So if you take up, if you add up this A term and B term, you will be getting omega t plus omega t, 2 omega t term, and theta V plus theta I. Okay, so this is how it looks like. This is how it looks like. So if you see the power component, this power component P of t has Vm Im by 2 into cos of theta V minus theta I. This is one term. Okay, minus Vm Im by 2 cos of 2 omega t plus theta V plus theta I. This is one more term. Now why I'm stressing on this point is, here this term is independent of frequency. Omega term is not there. Okay, so right, even though the time changes, this term is not going to be changed. So this is going to be a constant term. But when it comes to here this is a double frequency term. All right. Now let us draw the graph. So that I can tell you the deflection of the pointer. How will be the deflection of the pointer? Okay. So if I draw a graph, the power curve will be like this. P of t will be on omega t, or otherwise just t if you take up. There will be one constant term, and this height is around Vm Im by 2 into cos of theta V minus theta I, because it is not going to change with respect to time. But the other parameter is there, 2 omega t term. So that is minus Vm Im by 2 into cos of 2 omega t plus theta V plus theta I. So I am just drawing in a rough manner. As it starts from minus. So let us take up it as negative term. If it is okay, let us take up it as negative term. So maybe negative like this. Okay, so this is Vm Im by 2 cos of 2 omega t plus theta V plus theta I. Okay, so this is the double frequency term. Now this waveform, is going to be applied to the meter which is connected between source and load. Now please try to understand here. If I have a meter which consists of current measuring coil, that is current coil, and voltage measuring coil, that is called as pressure coil. So this is going to measure load voltage, and this is going to measure load current. Now connect this current measuring coil in series with the load. And this is the supply. Okay, so this supply V of t is going to drive a current through the current coil, and the current is flowing through the load. So whatever the current coil purpose is to measure the load current only. It's like an ammeter. Now pressure coil purpose is to measure the voltage across the load. Now whether you can connect the pressure coil maybe like this, or otherwise like this also. If you connect like this is after the supply pressure coil is connected. So that is, it is like a voltmeter, and then current coil, it is like an ammeter. So it is looking like voltmeter ammeter method. Whatever I have drawn in the first case, connecting here and connecting here, that is, what I can say, that is ammeter voltmeter method. Okay, generally this connection is much popular. We call this as main terminal, common terminal, and this is load terminal, and this is pressure coil, that is voltage terminal. MC short is much popular rather than LC short. Okay, now pressure coil is going to measure the voltage, current coil is going to measure the current. Anyhow, if you see, I know the current flowing through the current coil, that is IL, but current flowing through the pressure coil, I can write it as IPC. Now both the currents are going to set up the magnetic field. Both the currents are going to set up the magnetic field here and here. Now whenever you have two magnetic fields, now the two magnetic fields will interact and create a torque on a moving system. So you can create a torque on the, you can get a torque on the moving system. Out of these two coils, which coil is a moving system is a question. Generally we place current coil as fixed system and pressure coil as a moving system. This is a moving coil and this is the fixed coil. So on the moving coil we will be having a pointer like this. Okay, now whenever this kind of power component is drawn by the load, we will be getting a deflection due to the constant term. We will also be getting the deflection due to the double frequency term. Okay, on an average, how much deflection is going to be taken place by this wattmeter is a question. On an average, what is the deflection of this meter is a question. So if I have, if due to this component, we will be getting a constant deflection according to proportional to that value. But what about this one? This one, for positive half cycle, positive deflection. For negative half cycle, negative deflection. On an average, over a particular period of time, the net deflection due to the double frequency term is going to be 0. The average power contributed by this term, is going to be 0. Now the only power available, or the only power which we are going to see, or which we are going to measure, is this term. That is the reason why the average power is given as simply Vm Im by 2 into cos of theta V minus theta I. We also write the angle between the voltage component and current component is actually power factor angle. This one, the angle between voltage component and current component, theta V minus theta I, this is taken as power factor angle or load power factor angle. Okay, I can also write this Vm by 2 as Vm by root 2, Im by 2 as Im by root 2, because root 2 into root 2 again you will be getting 2 only. So cos of phi. So we will be writing this as Vrms, IRMS and cos phi. So this is the average power which is consumed by the load. This is the average power which is consumed by the load. Okay, right. So this power has to be, this is consumed by the load. This power is consumed by the load, and this power has to be indicated by the wattmeter. Or this power has to be indicated by the meter. The meter purpose is to represent this power only, na? So this is the true power. This is the true power. Okay. Now we have to design a meter such that it has to represent this, Vrms, IRMS, cos phi. Let us see whether the meter is going to deflect or represent this power or not. That is measured power. Okay, measured power. So let me show you here. To get measured power almost equals to true power, how will you design the meter is a question. So the current coil purpose is to measure the current only. It should not result any voltage drop. Current coil purpose is to measure the current only. Therefore, we should design the current coil such that the voltage drop across the current coil should be as minimum as possible. The voltage across the current coil should be, the voltage drop across the current coil should be as minimum as possible. Negligible, we can write it as negligible. Okay, how to design that to get less voltage drop? You know, if you want to design the current coil with less voltage drop, use less number of turns. Generally, the current coil is designed with less turns. If you design with less turns and huge area of cross section, therefore here less turns and large area of cross section, R is proportional to L and inversely proportional to area. If area of cross section is more, resistance is less. If length of the turns are less, resistance is still less. So the current coil resistance is going to be as minimum as possible so that the drop is going to be 0. If the drop is going to be 0, you see now here, the supply voltage and less drop is equals to load voltage. The load voltage is equals to supply voltage. If you write a KVL, see, if you write a KVL like this, load voltage equals to supply voltage because current coil drop is almost negligible. Current coil drop is almost negligible. Okay, so to get PM equal to PT, you have to design current coil with low resistance. Therefore, load voltage will be almost equals to phase voltage or supply voltage. Okay, generally the current coil is made as fixed coil. This is very important point. Current coil is made as fixed coil. Why? Because it is carrying load current. Generally, load currents are large values. You know, if it is made as moving, from a moving system, tapping the current is little bit difficult. From a moving system, if you are trying to tap the current, you will get sparks. So to avoid the sparks, generally current coil is made as fixed coil to avoid sparks. Okay, now coming to the pressure coil, you know, pressure coil has to measure voltage only. So to get load voltage, it has to be designed with high resistive nature. Pressure coil should be designed with high resistive nature. RPC should be very high. RPC should be very high. I'll tell you what is the reason behind very high resistance. If it is highly inductive nature, it is going to measure reactive power. If it is highly resistive nature, it is going to measure active power. That's it. Okay, let me show you. If it is highly resistive, how it will be. If it is highly inductive, how it will be. Let us see one phasor diagram. Okay. So this is my load voltage, which is almost equals to the supply voltage because the current coil drop is almost negligible. Okay, I am taking the load. I took the load as lagging load. If the load has lagging load, now the current flowing through the current coil is lagging with respect to load voltage by some power factor. This is load power factor angle. So current coil current is equals to load current. Now what I should get? I should get pressure coil current also. No, as a pressure coil, we have designed the pressure coil with highly resistive nature. So generally, this is how it looks like. Current coil, and this is pressure coil. So pressure coil is of highly resistive nature. ICC and IPC. So if it is highly resistive nature, the pressure coil current will be in phase with the pressure coil voltage. What is the pressure coil voltage? The pressure coil voltage is almost equal to supply voltage now. Supply voltage, pressure coil voltage, load voltage almost same because the drop in the current coil is almost 0. So this is where the pressure coil current looks like. Now the pressure coil current is going to create pressure coil flux lines. Okay, current coil current is going to create current coil flux lines. Now between these two flux lines interaction takes place and therefore the torque creates, and that torque is useful to move the moving system of the EMMC meter. Okay, what is the angle between IPC and ICC? Phi, simply. The angle between IPC and ICC is phi. So whatever the deflection torque we are going to get, the deflection torque is always proportional to current flowing through current coil, current flowing through pressure coil into cos of angle between current coil current and pressure coil current. And this is what we write: current coil current is equals to load current. Pressure coil current can be taken as VPC divided by RPC. And now the cos of angle between ICC and IPC is equals to load power factor, cos phi. Okay, so if you see here, generally RPC is very high and it is made it as constant. So this is anyhow it is constant. So let me show you. The deflection torque is proportional to IL, VL. VPC is nothing but VL na, load voltage na, into cos phi. So the deflection torque obtained by the meter is load voltage, load current and load power factor. This is what measured power. So measured power is almost equals to true power. This is how we will be getting the indication by the electromagnet moving coil instrument as almost equals to the true power consumption. It is possible only when you make RPC as very high or purely resistive nature. It is not to say exactly very high, it is purely resistive nature. If it is not purely resistive nature, then the current coil, then the pressure coil current lags with respect to voltage by some angle. Therefore, the angle between pressure coil current and current coil current will not be phi, it will be less than phi. So if the power factor, if the angle reduces, there might be increase in torque. So the measured power may be greater than the true power. You may get deviation again. You will get deviation again. So that is what, this is how we design the wattmeter, electromagnet moving coil meter, and the power measurement is going to be this is the power measurement. Single phase power equation is RMS voltage, RMS current, or simply V phase, I phase, RMS values only, VL, IL, cos phi. Okay, to measure this component, we are designing a meter with current coil and pressure coil. So how do you design the current coil? The current coil should be designed with low resistance to get VL equals to V phase. Pressure coil should be designed with should be a purely resistive nature. Then only measured power is equals to true power. If it is very high, I can say measured power greater than the true power. There will be chance of error again. Okay, so this is what measurement of single phase power, and the point you are going to get is the question you are going to get it is you can get the question from the average power calculation. Okay, right, and they will be asking, sometimes they will give you the diagram. Is it equivalent to ammeter voltmeter method or voltmeter ammeter method? Well, that kind of questions also they'll ask you. So let me show you. If current coil is here, this is nothing but ammeter. If voltage coil is here or pressure coil is here, this is nothing but voltmeter. And if I connect like this, ammeter is generally connected in series with the load, and voltmeter is connected in parallel with the load. So here after the supply, voltmeter is first. So it's like a VA method. So MC short is like VA method. Okay. LC short will be, this is L and this is C, this is M and this is V. Okay, so LC short, after the supply ammeter is first, and then after the ammeter this pressure coil, that is voltmeter. So LC short is like ammeter voltmeter method. Okay, so the same kind of errors you will get. Here we got error due to ammeter na, so we got error due to current coil. In MC short, error is due to current coil. In LC short, error is due to pressure coil. Same like again, it's like I can write it as IL square into RCC, and here the error is going to be VL square by RPC. Okay, right. So it's like single phase, the watt meter or otherwise, EMMC meter is same as like MC short watt meter or LC short watt meter. Is same, looks like MC short looks like voltmeter ammeter method. LC short looks like ammeter voltmeter method. Okay, so these are the points you need to understand from this session. Okay, if you have any doubts, you can ask me. If you have any doubts, you can ask me. There is a crash course announcement. Those who are preparing for GATE 2024 examination, not just ECE but also for EEE also. Okay, so this crash course will help you to strengthen your concepts and fundamentals. Right. We are going to focus more on the theoretical part along with the problems also. So this is my Telegram channel. You can join here and ask me for the doubts or any announcement. You can join here and you can you can get the notifications. If you want any PDFs or subject textbooks, you can ask me. Okay, right. So that's my Telegram channel. And coming to this, if you have not yet subscribed to BYJU'S Exam Prep YouTube channel, you can subscribe by clicking on the bell icon. If you like the session, just hit like button. Okay. If you subscribe, then you will get notifications about the classes which are going to happen on the BYJU'S Exam Prep platform. Okay, all right. That's all from my side. Anybody? Any questions? Any general questions? All right, then. Have a nice day then. Bye bye. See you.